I'm not going to show you many equations here, but this is useful just to show you that this says that the energy density is proportional to the energy of the light, and there's a temperature dependent term. So this tells you that there is a temperature dependence because this is radiation that comes from hot objects, warm objects, and it's all over the place. But then 11 years later, he realized that this theory was incomplete and didn't completely describe the data. And so he came up with his second theory. And in the second theory, he added another term that's temperature independent. And this, it turns out, is zero-point energy. This was largely ignored by the scientific community for a decade or two until the development of quantum mechanics, of which Planck was really the grandfather. And with the development of quantum mechanics, the whole concept of the uncertainty principle came up. We'll be talking about that. And the uncertainty principle then once again gave rise to zero-point energy. And that's when the general scientific community accepted that there does seem to be some sort of a zero-point energy. So what does this mean? If you take a look at the energy density, the amount of energy that there is in free space as a function of photon energy, so this is how much energy each particle of light has, you'll see that there is this thermal background radiation. And this is the thermal background radiation at room temperature, which is about 300 Kelvin. And at room temperature, the background radiation peaks roughly here. So this goes from the far infrared to the near infrared, visible light, and then ultraviolet light. And so we can see that the radiation from the temperature around us, the temperature of the Earth and everything we see, is dominantly in the infrared. And that's why we don't really see it. But then there's this additional factor, and this additional factor is the zero-point energy. And the zero-point energy increases dramatically. It increases with the cube of the frequency. And quite quickly, by the time you get into the visible and ultraviolet, it completely dominates what the background radiation is compared with the zero-point energy fluctuations. Compared with the thermal background. Okay, so what is this vacuum energy? So zero-point energy fills all space and matter. It was proposed by Planck, as we saw, and then later codified by the uncertainty principle. So the basic idea of the uncertainty principle is that you cannot know to absolute precision two different types of variables at the same time. So for example, you cannot know the position and the momentum or velocity of a particle, both of them to absolute precision. If you know the momentum more, you know the position less, and vice versa. So one of the implications of this is that no particle can stand still. Because if a particle stood still, you'd know that it wasn't moving and you know where it was. And so everything wiggles. Everything has to wiggle in quantum mechanics. And not only does everything wiggle, but also free space itself wiggles. And by that I mean that there are electromagnetic radiation that appears and disappears and appears and disappears in free space, and a lot of other phenomena that occur and then are annihilated in the vacuum. And this uncertainty principle can be expressed in terms of an uncertainty in position and momentum or velocity. You can also express it in terms of time and energy. So the more precisely you know when something is there, that you can measure it, the less precisely you know its energy. So in other words, the more energy it could have. And we'll talk about this uncertainty principle a little bit more in the future. But the basic idea I want to take home right now is that these fluctuations occur for a very short time. Okay, So what are the issues in harvesting zero-point energy? There are really three main issues that I've put together that really are the objections from the scientific community, saying that you really cannot harvest it and use it. One of these says that it's the universal background state. Everything has zero-point energy, and therefore there's no tilt to it, there's no flow to it, it's uniform everywhere. The second one is that it's an equilibrium state. And so in order to harvest it, you'd be violating the second law, as I mentioned earlier. And then the third problem is that if some way you could, there's still the problem that these fluctuations that form the zero-point energy are very short-lived. They're extremely short-lived. So how do we get around this? Can we modify the ground state so that it's not uniform everywhere? Well, it turns out that for zero-point energy, you actually can. And that is that the vacuum state depends upon the structure around it. In other words, it's geometry dependent. So this would be as if you could have an ocean with a flat level, and then one region of the ocean would just have a dent in it, a well in it, that was lower than everywhere else. Oddly enough, you can do this, and it's been demonstrated with a zero-point energy. The way has to do with a structure called a Casimir cavity. So in 1948, the physicist Casimir was doing some mathematical analysis on having two closely spaced mirrors. And he said, if there are two closely spaced mirrors, that means that you'll only be able to have a certain number of modes of wavelengths within this closely spaced Casimir cavity, but outside you could have all sorts of wavelengths. So this is, think about it like a guitar. So a guitar string is pegged on both ends, and therefore it just vibrates at a fundamental frequency in its harmonics. Same thing with zero-point energy. Inside a Casimir cavity, all wavelengths that don't meet the appropriate boundary conditions are suppressed. Another way of looking at it is that it suppresses all long wavelengths. So any wavelength greater than twice the spacing of the cavity ends up being suppressed, and other wavelengths are permitted. So Casimir came up with this concept, and one of the predictions he made is that because there'd be more zero-point energy radiation outside the cavity than inside, there'd be a radiation pressure that would push the cavity walls together, and these two plates would be pulled together. So he predicted this in 1948, and it wasn't for several decades, and really until the end of the 20th century, that it was measured accurately, and he was right. And so these Casimir cavities do in fact have plates that are attracted together. This only happens for very, very closely spaced plates, and it happens only, it's a fairly small force. So these plates need to be less than a micron apart, a millionth of a meter, and the force is tiny. Okay, so we now say that yes, we can modify the ground state. But then we have the problem of equilibrium and the violation of the second law in trying to harvest zero-point energy. So is there some way around it? Is there something we can do to get around it? Well, by answering the third objection, maybe we'll find a way. So that has to do with extremely short-lived fluctuations. So before I go there, I want to tell you about equilibrium and detail balance. So equilibrium means that everything is in harmony and there's no net motion anywhere. But there can be motion, and there can be particles and energy moving. So for example, if we have a system that has three parts, here I'm labeling them A, B, and C, there can be energy flow from A to B, but there is a detailed balance in which the energy flow from A to B is exactly balanced by the energy flow from B to A. And the same thing between all the other parts of this system in equilibrium. And if this weren't true, what would happen? If it weren't true, then we might have a net flow. For example, if zero-point energy everywhere were absorbed by a leaf, and a leaf is a nonlinear material, and so the leaf is going to take these zero-point energy fluctuations and down convert it into heat. And so we'd see hotspots all over the place on leaves and every other sort of nonlinear material within our universe, but we don't. Why do we not? Because there's a detail balance. In other words, whatever might be producing heat, the reaction also goes in the other direction, and we don't. Can we break that detail balance? And so here we come back to these extremely short-lived fluctuations. So this gets into the notion of, again, the uncertainty principle, but the delta E, delta T, that is uncertainty in energy and uncertainty in time. And there has been proposed by a physicist, Larry Ford, that there's a quantum inequality. And the quantum inequality says that an energy, delta E, may be borrowed from the quantum vacuum for a time, delta T. Then it has to be repaid, and it has to be repaid with interest. So how long can you borrow the energy and how much energy? Well, if it obeys the uncertainty principle, and it's not clear it does exactly, but if it does, that would mean we could borrow, say, a photon, a red light photon's worth of energy for a tenth of a femtosecond. Now, femtosecond is extremely small. It's a 0.15 zeros, 16. It's an extremely short time. But during that time, we can violate the first law of thermodynamics. That is, we can actually get energy out of nothing and we can see it, but then it's got to be returned. Okay, well, if we can borrow it, could we be sneaky and could we borrow it and capture it very quickly? And if we could borrow it and capture it very quickly, then could we skirt detailed balance? And this was what I was thinking about as I was trying to come up with a way to harvest zero-point energy. And the way that I thought we should try involves metal insulator metal diode. So let's talk about that. If you have a metal insulator metal diode, so you've got a piece of metal, a very thin insulator, and this is going to be a couple of nanometers thick. That means about 10 interatomic distances or so thick, and then another metal. You can excite electrons on one side, and those electrons tunnel through this forbidden region of the barrier or the insulator and get captured on the other side. And once they're captured on the other side, it's very unlikely that they'll be able to go back again. And so in this way, we might be able to very quickly capture zero-point energy, because this tunneling process takes place on, takes about a femtosecond or so to occur. And so we might be able to absorb some of that zero-point energy. So I thought, okay, how are we going to do that? Well, let's take a look here at the concept. So we've got a base metal, thin insulator, and an upper electrode. And this upper electrode is very thin. It's so thin that if radiation, any sort of radiation, is absorbed, light is absorbed, it creates hot carriers. And these hot carriers, or hot charge carriers of electrons, then can travel through this thin upper metal electrode before they're absorbed, and then they can tunnel through or go over the barrier that's between the upper metal electrode and the lower metal electrode. Now, if this metal insulator metal diode is just sitting out in free space, there's also going to be the opposite current, because there will be internally generated hot electrons from the same sort of 0-point energy or whatever is producing it out here, and they'll cause a current to go the other direction, and there'll be no net flow of current. But what happens if we do something? Now what happens if we add to this a Casimir cavity? So we're adding to this a Casimir cavity on top. And we know, we just found out that a Casimir cavity reduces the allowed wavelengths in this Casimir cavity between these two mirrors, so that there's less energy here than there would have been in free space, because it restricts the vibrations on the guitar string, if you like. And so therefore, we're now going to have less radiation coming in. We'll reduce the current going this way, but perhaps the current going the other way will remain the same. And in that way, we might get a net flow of current from the base electrode to the upper electrode. So the actual device that we built is depicted here. So this is our metal insulator metal device using nickel palladium, transparent dielectric. It's too hard to make this out of vacuum, so we use either a polymer or a glass as our transparent material, and then coated with a mirror. And in this way, we're making our devices, and our measurement circuit probes current flowing between the base electrode and the upper electrode. This is a scanning electron microscope image of our device. They're very small. They're about 1/10 of a micron on one side and a little over 2/10 of a micron on the other side. So this was the concept I came up with, and I was working on it for quite a while, and my lab tried it furtively. We were doing other projects, so we really couldn't spend a lot of time with this. And it looked like maybe it was working, but it really wasn't very convincing. And finally, my technician, who's been with me for now about 3 decades, Dave Dorosky, and he said, "Look, Garrett, you really have got to give this a good try. Let's dig in and really do it right." And so he and a great postdoc in my lab, Ayendra Wirakoti, worked together and tried this. And they tried it with a number of different devices, and they tried it with a number of different configurations. And lo and behold, it actually seems to work. So we actually got power from the vacuum. So let me show you the way that we measure this. And this is measuring the current as a function of voltage. So this is the current, and this is the voltage. And we're getting out about, in this case, about 75 nanoamps, and it's at a voltage of a few 1/10 of a millivolt, or almost 1/10 of a millivolt. And the way that we can tell that we're getting power is this is the sort of current voltage measurement that's also done for solar cells. And there are 4 quadrants in the curve. So if your curve falls in this quadrant, as in up here, you're using power. If you fall in this quadrant, the 2nd quadrant or the 4th quadrant, then you're actually producing power, and this one is using power. And in fact, our devices put out about 70 watts per square meter, which is actually not bad for little test devices. That's close to what a solar cell puts out, which is perhaps 200 watts per square meter. And we then did this for different cavity thicknesses. Now, you know that the thinner the cavity is, the more modes it suppresses, because the thinner the cavity is, the more it suppresses all wavelengths that are longer than the cavity, than twice the cavity width. And so we're suppressing more and more wavelengths as we make narrower cavities. And that's just what we saw. As we made narrower cavities, either from the polymer or from the SiO2, we found that the narrower cavities gave us more current. So you say, well, maybe this is just some sort of electrochemical reaction, or there's some sort of a degradation mechanism that's just producing the current. It's like a little battery. So if you calculate that we have how many atoms we have in the insulator, it turns out that if one charge were trapped at every insulator molecule, the current we're seeing, 20 nanoamps, would take about 3.2 microseconds for it to deplete. But we see this current continuously. Here's a plot showing the current as a function of hours. And actually, we've done this for longer times. The current comes out and it just keeps coming out.